Hello, guys. Welcome to Cheenta School of Statistics and Data Science. We are a team of extremely passionate teachers, researchers, and statisticians from the top universities of India and US.
So let's try to solve this problem. An ISI MStat problem is very similar, like the basic fundamental problems of mathematics, probability, and statistics, not statistics much, but mathematics and probability are very similar to CMI and of course to IIT. So this year ISI MStat 2024 and problem number 26. Okay, so let's see what the problem talks about. This problem talks about the following. So there is a random variable x with the probability density function displayed in the following graph. So we have three information given. So one is x is random variable and its probability density function PDF is given. So to revise, what is a PDF? If x is a random variable, so a random variable is nothing but a function from the sample space to the real numbers, right? And for each and every random variable, there is an unique cumulative distribution function, CDF. Okay, and for that CDF, if that CDF is continuous, okay, or rather integrable, let's not go into much mathematics. So essentially that CDF has some properties, let's not go into that. That's unique, remember that. But if that CDF can be expressed as something like this, minus infinity to x, if for some fx dx, if that CDF can be expressed, then this is called a PDF. Now you can say, this is so complicated, but this is the true definition. What is done for easier thing, it's said that if this is differentiable, then by the theorem of calculus, I mean, if this is differentiable, you take the derivative on both sides, then it turns out that f dash of x turns out to be fx. Okay, but that's the outcome of this definition. Okay, but the definition is this, because this may not always be differentiable. Okay, for example, uniform distribution. So we are trying to understand each of the things in details. For uniform distribution, you know that for uniform distribution, the PDF is like this. So uniform distribution, it's 1 by 2. Let's say uniform 0, 1, 0, 2, if x is between 2 and 0, and 0 otherwise. Now, if you look into the f of x of this, the CDF of this, it's integrated. It will turn out to be nothing but like this. So uniform is like this. If you draw it geometrically, 0 to, so let me use a different color, 0 to 2. And if you take the integration of this, it will turn out to be, sorry, I did a mistake here, 0, 2 and half. Okay, and if you do an integration here, let me draw it in green. So here till here it's 0, and till here it's, if you integrate this area, if you're integrating, it will be kind of this, and then it reaches 1 and it constants. It's constant and it's right continuous, like CDF property. So you can see that, so you can define it as 0 if x is less than 0, and x if x is less than equal to, or I think it's x or something, x 2x. Yeah, 2x if x is less than equal to this. Yeah, is it 2x? Yeah. Probably x is, let me think. Okay, let's integrate. So it should be x by 2 ideally. X is greater than equal to 2. So, but you can see here that the CDF is not differentiable, okay, because there's a discontinuity here, and that's very, very important. The CDF is not differentiable, and hence f of x, this is not the general definition. The general definition is this. Okay, all of you understood this definition? It's just a recapitulation of the entire idea, so that I don't know whether it will be used here or not, but it's important to get the definitions correct. So let's see what is the question that is asked. It's asked that match the following random variables with respective probability distribution, density functions, sorry, or distributions. Okay, so essentially there are 4 random variables given and 4 plots given. The x is defined here. So it's asked to match the following. Essentially, you have to understand how the density is moving or changing. Okay, so let's see. So here understand at 0, it's coming around this 0.05, at the maximum is 0.02, and let's see, okay, it's kind of minus 2.5 or somewhere in between. So you can easily understand that. So now the question is, if fx, this is the distribution of x, Then what is the distribution of f of x plus 3? What is the distribution of f of x plus 3? Or what is the distribution of f of x minus 3? And you can see it's nothing but it's similar, because so essentially these two options are asking. So there are two kinds of thing you can see. Essentially it's asking what is the distribution of f of x plus c for some constant, and also what is the distribution of f of x times c for some constant, right? Because c here is 2 half, and here c here is minus 3 and 3. Okay, so we are need to understand that what is the relationship of this distribution with this distribution. Okay, basic general idea. But we can do it mathematically, but can we do it intuitively? Yes, so we can do it intuitively, and you can see that it's not very hard to do, at least for this location change where x is changed by a constant. Because if x is changed by a constant, so you can think about like this. This is the way to think. Let's say this is where it becomes helpful. So what is the physical interpretation of this? Of course, this density is not a probability, right? But this density has some relationship to the probability. Why it's not a probability? Because it can go above 1, right? Yes, so the density property is that integration minus infinity to infinity f of x dx is equal to 1. Why can we take integration of this f of x dx? Because it's said that f of x can be integrated. That's how the definition is. So this is 1. So then the question is that, can fx take a value more than 1 or less than 1? Yes, it can take a value more than 1, because imagine a thing like this. Like this needs to be huge height so that the area becomes 1. Okay, if it's like a sharp probability distribution. So the height can be 1. This is a very important concept. So, but the question is that if the fx height, the fx value, the small fx value can be greater than 1, what is the relationship with the probability? This should be having some relationship with the probability, right? The relationship is in the following. The relationship is the following. So if you take any x, small x, and if you take a small dx, let's call it x plus dx, and if you take this height, then the area between this, okay, this area, that is what you can write it as. You can write it as integration of, or you can write it as the height is around f of x, because it's dx, and the breadth is dx, and the height is f of x. So the area is around f of x dx. Okay, the area is around f of x dx. So since the area is around f of x dx, this is the area around x. So essentially it's saying this is nothing but this is the probability. This, since the area under the curve, so this is the probability that x is taking a value between x and x plus dx. Okay, this is important. So x is taking value between x and x plus dx. All of you understood this? Yes or no? F of x dx is nothing but saying that x is taking value between x and x plus dx, because we have taken the area under the curve. X is taking a value between x and x small x plus dx. This is nothing but this height. And if you want to do it in terms of CDF, it's nothing but f of x plus dx minus f of x. Why? Because this is CDF is nothing but probability x is less than equal to x plus dx minus probability x is less than equal to x. So if you subtract this, you will get it's nothing but probability x is between x plus dx and x. So that's exactly what you get. And from here also you can derive the derivative of it. That is f of x plus dx minus fx is equal to f of x dx. So you get that f of x plus dx minus capital of fx divided by dx is nothing but fx. And as dx goes to 0, this is nothing but f dash of x, right? Which is nothing but this relationship. So this is valid. Okay, so what I mean is this, that the area under the curve between x and x plus dx is nothing but almost equal to f of x plus dx. So let's duplicate. And why I duplicate it? Because it's important to have all this information out here. Okay.
If you're enjoying the video, show some love by liking the video and subscribing to the channel. We welcome you again to this passionate community of budding statisticians and data scientists. Let's enjoy the rest of the video. Stay tuned and stay blessed.